Okay, so momentum. Now, the key thing here is if we have some sort of collision with one ball going towards another with some velocity, when they collide, they will kind of bounce off each other, and some of the velocity will go into the second one. So you can imagine it like pool balls. If that one was stationary, this one comes along, it might bounce into that one, and at the moment after the collision, maybe the red one's travelling slower and the yellow one's travelling off towards the right. It might be that when this one collides, that it has enough impulse to send it backwards, and they'd end up like this. Or it might be that as they collide, they kind of combine together and they go off together like that, or some situation like that. Now, the key formula here is that momentum is conserved after a collision. Now, this is one of the things I say with a few asterisks on it. For now, this formula will be true. When you consider that the materials might have some sort of deformation go onto them. So imagine a car has a crumple zone at the front of it as it hits another car. Some of the energy will go into one of the objects, and so this formula won't be true anymore. However, for now, we're going to take it as it's pretty much true. It's only true. It's only not true if some sort of energy is lost, maybe in heat or plastic deformation or elastic deformation or that sort of thing. Anyway, the quantities here, M1 and M2 are the masses of each of the objects, so it could be like a mass of this object, like that. U1 and U2 are the initial velocities of each of them. These are velocities rather than speeds, so the direction matters. A minus number just means it's going in the opposite direction. And then V1 and V2 are the final velocities of those objects. Okay, so let's have a go at a particular question with these. They all look very similar. Here is a before picture. So we've got two objects, say this red ball over here, I've given it a mass of 3 kilograms, and this yellow one is heading towards it with a velocity of 3 meters per second. This one's stationary, and it's got a mass of 2 kilograms. We've also got a bit of a snapshot of the after picture here, so let's just move the balls. The after picture, very similar, we've still got the same balls, so 2 kilograms and 3 kilograms. After the collision, this 3 kilogram one is now moving with a velocity of 7/3 meters per second. And this one over here is going at V meters per second. The first thing to do here is work out what V is. Well, we can work out the momentum before and the momentum after. So let's work on the before first. Momentum is the mass times the velocity. So the momentum of this one would be 6 kilogram meters per second. The momentum of this one, it's got 0 velocity, so its momentum is 0. And so the total momentum before was 6. If we try it on the other one, the after picture, well, this one has a velocity of 2v. We don't know what v is, it's constant we can solve for. And this one has a velocity, well, 3 times 7/3 is 7. And so it has a total momentum there of 2v plus 7. Putting equal to the momentum from before, we have 6 equals that, and we can solve it. So 2v equals -1, and so v equals -1/2. What that's saying to us is if we had this one fired in at 3 meters per second, it will then bounce off, and so afterwards it's got velocity actually going towards the left. It's ricocheted off, like the white ball in pool or snooker often does. This is measured in meters per second. The other part of the question we're going to do, we mentioned impulse in the first video. The impulse you can think of as the change of momentum. We can do the impulse on a particular object. So if we were trying to do the impulse on, say, the 3 kilogram ball, its momentum before was 0, its momentum after was 7, and so its impulse would be 7 Newton seconds. If we try doing the impulse on the other ball, well, its original velocity was 3. Its initial momentum, we'll do it like this, is 6. Its momentum afterwards, well, if we put a v in as -1/2, its new momentum here would be -1. And so the change in momentum would be 7. I've just made that a positive number. I know it comes out as -7, but you can think of impulse as we want a scalar here. And so it's 7 Newton seconds. You'll notice that it's the same number either way. And so if it's asking you for the impulse on an object, you can work it out for either of the two objects, and they will be the same. often there will be an easier object and a less easy object. So if you've got something that is massive, so let's say you're bouncing a ball against a wall or something like that, you would always deal with the non-massive object, you'll deal with the ball. Same if you've got someone hitting a tennis ball with a tennis racket, say, you would deal with the ball rather than the tennis racket. This is pretty much it. The way that I lay out these questions is I will draw out a diagram exactly like this with a before and after. I will label on everything I know, and then I'll look to see if there's any letters that I don't know. In this one there was just a V. Sometimes you might have simultaneous equations to do to solve them. The key formula is always just this one. Momentum before equals momentum afterwards in a collision. Again, there's some caveats on that, but we're not going to worry about it for now. Okay, you should have enough to be able to go have a go at lots of the exercises now. So in the textbook, I'll give you a clipping of this. But exercise 1B has lots of questions like this. If you want more examples, I've gone through example 5 in the book, but example 6 and 7 are there. They're very similar. Cool.